Welcome to the second session of vectors. Last session we had basically started with the concept of introduction to vectors, and I had basically discussed about type of vectors. We had discussed position vectors. We have discussed how position vector was helpful in applying coordinate geometry concepts to solving vector questions. We also had talked about the addition of vectors. So today I'm going to just finish the introduction part, because we are going to start with the more serious part like dot product, cross product, vector products, scalar triple product and vector triple product, etc. But of course, in today's class, I will not be able to go to that extent. I may be able to just cover up vector product with you. So initial part, I'll be talking about something very important and very much ignored in the school, which is called the concept of linear independence and linear dependence. Linear independence and linear dependence and linear dependence. Linear dependence. Okay, many of the operations that you would be doing in vectors, okay, you do it because of this concept that we are going to study now. Even though it is not mentioned, or even though we don't have any context that we are using this kind of theory to do a lot of activities. Okay. For example, if I ask you this question, I think most of you will be able to answer this. Xi plus yj is equal to 3i plus 4j. Okay. I think we had done a question like this in the last class when you were talking about one man traveling towards east and the wind is blowing. All those questions, right? So here, what will be your x and what will be your y? What will your answer be? Of course, your answer will be x is 3. Correct? Y is 4. Right? Right? And nobody challenged this. Right? So we just say, okay, compare the coefficient of x with I with I, compare the coefficient of j with j. Right? But actually, the answer to this comes from the concept of linear independence and linear dependence. So things like this, which we take for granted while we are solving vector question, has a deep-rooted concept behind it, which is the concept of linear independence and linear dependence. So before I start the concept, good afternoon, Sai. Before I start the concept, I would like to talk about linear combination. This word also you will hear from me very often, linear combination. Okay, now what is linear combination? See, a vector R, let's say, a vector R is said to be a linear combination, is said to be a linear combination of vectors a1, a2, etc. till let's say an, if there exists scalars m1, m2 all the way till let's say mn, such that you can write R as follows. Okay. Now this concept per se is not that important, but yes, I'll be making reference to this word linear combination every now and then. So you should know what do I mean by it. So when such a case happens, we say R is expressed as a linear combination of A1, A2 till AN vectors. Now this is a prerequisite to understand the concept of linear independence and linear dependence. So again, revising it, whatever we had discussed in the last 5 minutes, because some of you have joined late. So today we are going to talk about the concept of linear independence and linear dependence. Okay. And before we start the process, we need to know what is the meaning when I say R is a linear combination of certain vectors. When you say R is a linear combination of, let's say, A1, A2, A3 till AN vectors, that means there exists some scalar quantity M1, M2 till Mn such that R can be expressed like this. Okay. Now, what is linearly independent vectors? So let me start with the first part over here. Linear independence. So linearly independent vectors. A system of vectors. A system of vectors. Now, please make a note of this. A system of vectors A1, A2 till AN is said to be linearly independent. Is said to be linearly independent if a linear combination of these vectors, now see, I'm using the word linear combination, so you should know what I'm talking about. If a linear combination of these vectors expressed to a null vector implies that all these scalar values are actually zero. All these scalar values are actually zero. That means if you try to take a linear combination of linearly independent vectors and equate it to a null vector, this can only happen when each of these scalar quantities over here are individually zero. Okay. Such vectors are said to be linearly independent. I can give you an example of it. Let's say your vector A1 is your I cap, A2 is your J cap. These are examples of linearly independent vectors. Now, let me explain to you this in a very simple language. So what it tries to say is that if you make a linear combination of these two vectors, let's say I take M1I, M2J and equate it to a null vector, this can only happen when M1 is equal to 0 and M2 equal to 0. Why? Because no matter what, see, what is the meaning of multiplying I cap with M? That is called scalar multiplication, right? So when you're multiplying I cap with M1, you are trying to either reverse its direction or try to scale up and down the magnitude of I cap. Okay, or both can happen together. Similarly, M2J means you are trying to either reverse the direction or trying to scale up or down the magnitude of that vector. Now, whatever you do, you will not be able to make a null vector out of it. See, let's say I cap is this way, J cap is this way, right? No matter whatever you do with these vectors, you scale up or scale down, right? Right? This also scale up, scale down, reverse the direction. Unless until you make both of them become 0, 0, your sum will not become a 0. Are you getting my point? So this is what we call as these two vectors being linearly independent. That means you will not be able to complete a closed path with them. Are you getting my point here? So no matter what you do with this vector, okay, in terms of scaling up or down its magnitude or reversing its direction or maintaining its direction, no matter what you do with this vector, in terms of scaling up or down its magnitude or changing, reversing the direction or maintaining the direction, you will never be able to create a closed path. Are you getting my point? Okay. Yes. So now a question will come. Give me an example or what is an example of two such vectors which will be linearly dependent? Okay, now I'll give you an example of linearly dependent. Okay, of course, I'll come to the definition of it also. So let's say on the other hand, if I talk about 2i and I, then these are linearly dependent. I'll come to the definition, but I would like to express a very simple concept over here. Dependent. In this case, if you have I vector and you have another vector 2i, right? Can you do something with these vectors such that the resultant becomes 0? You will say, yes, sir, I can do that. I will scale this up by a factor of 2, okay, and reverse this direction. So I'll make minus 2i cap from it. That means I'll scale this up 2 times and reverse this direction. Now try to add these 2 vectors. Now if you add these 2 vectors, you will be able to get a null vector out of it. That means the value of m1 and m2 here are not both 0. Are you getting my point? The value of m1 and m2 here are both not 0. M1 and M2 are not 0. And still you are able to generate a null vector out of it. So this would be example of linearly dependent vectors. So officially, let me give you the definition. So linearly dependent vectors are basically, let me write it down. Yeah, I'll write it down over here. Linearly dependent. So a system of vectors a1, a2, dot, dot, dot till an is said to be linearly dependent, if there exists scalars or scalar quantities m1, m2, dot, dot, dot till mn, okay, not all 0. I'm writing this in not all 0, okay, such that you can use those scalar quantities to make a linear combination of these vectors become a null vector. Okay, this is very important, not all 0. Right? So there is some scalar quantity, right? Not all 0, such that a linear combination of a1, a2 till an can be expressed as a null vector without making these all as 0. So there would be some non-zero m1, m2, etc. values also in this case. So this is the example which I was basically explaining to you in that regard, that there is an m1 value, m2 value. In this case, both will not be 0. Okay. And you can still obtain a null vector by its linear combination. That means you can create a closed path by, playing with the magnitude and direction of these 2 vectors here. Is this concept clear? What is the meaning of linearly independent and linearly dependent? Because the same thing now will be used up for you to understand the concept of collinearity and coplanarity, which is going to come up, and at least we are going to talk about it for 1.5 hours in today's class. Right, Venkat? Yes. What if some are 0 and some non-zero? I didn't get you.
Sir, if sometimes the coefficients become some as 0 and some as non-zero, they'll still be linearly dependent, no, sir?
Some of them. All of them should not be 0.
Okay, sir. Okay.
Yes. Some of them can be 0, but not all of them.
Okay, sir.
Okay. Now, what is important is for us is to understand few theories related to it. Why are we actually learning this concept? Okay. How is it related to vectors? or how is it related to our understanding of vectors? Okay, so linearly dependent independent concept is clear. Now there are certain theories that we need to understand, certain theorems which we need to understand, which is connected to your linearly independent and linearly dependent concepts. Number one, a pair of non-collinear vectors. Now don't ask me what is the meaning of non-collinear. What is the meaning of collinear? When are two vectors said to be collinear? When they are on the same support or parallel supports. Remember last class we had talked about collinear vectors. So the type of vectors, please recall that concept. So a pair of non-collinear vector is always linearly independent. Remember I gave an example of I and J. I knew they were non-collinear and hence I could safely say they were linearly independent. Now what is the proof for this? Why? The question is why? Okay. Why a pair of non-collinear vectors are linearly independent? Okay, let me give you an example. See, first of all, what's a collinear vector? In a collinear vector, you can express one vector. Let's say vector A is collinear to vector. Let's say A1 is collinear to vector A2. Then we know that if they're collinear, you can express this as a scalar times the other. Isn't it? Yes or no? Okay. Now, if there are two non-collinear vectors, so if A1 and A2 are non-collinear vectors, and I try to express a linear combination of these two and equate it to null vector, right? Then see what will happen. If I say M1 and M2 are not equal to 0, that means I have considered them to be linearly dependent. Then see what will happen. A contradictory situation will be created. Now from here, can I say I can write A1 to be minus M2 by M1 A2? Correct? But if this is the case, it can only happen when the vectors A1 and A2 are collinear. But it is given to us that A1 and A2 are non-collinear vectors. That means this can only lead to M2 being 0. Are you getting my point? Correct? Because there should not exist any non-zero scalar quantity by which I can express a vector A1 as a linear combination type A2. Similarly, A2 can be expressed as minus M1 by M2 times A1. But again, this will violate the condition of A1 and A2 being non-collinear, because if you can express A2 as lambda times A1, then they must be collinear. But that is not the case, which means M1 should also be 0. Correct? So what I did was I'll say let A1 and A2 be non-collinear vectors. Now what I'm trying to prove is that such a non-collinear vector would be linearly independent. This is what I want to prove. So what did I do? I started with a linear combination of these two vectors, equated it to null vector. And I realized if this is the case, I can express A1 as lambda times A2, or A2 as lambda times or some beta times A1, both indicating to the fact that A1 and A2 are collinear, but this is not. So if this is not, that is they're non-collinear, that means only option I have is that M1 and M2 both should be 0. And if M1 and M2 is both are 0, then from here I can only conclude that M1 is 0 and M2 is 0, clearly indicating to the fact that they are linearly independent. They are linearly independent. Okay. So this is theory number 1, or theorem number 1, which is associated with linearly independent and linearly dependent concepts. So a pair of non-collinear vector is always linearly independent. So please remember, if you are trying to express, so the conclusion is, if you are trying to express a linear combination of these two vectors as a null vector, okay, where x and y are scalars, okay, and if it results into the fact that x1 and x2 both are 0, then you can safely conclude that A and B are non-collinear. A and B are non-collinear. So this is used as a test for non-collinearity of two vectors. Are you getting my point? And if x and y are both not equal to 0, right? See, if A is a non-zero vector and y becomes 0, you cannot have x not equal to 0. X will definitely become a 0 in that case. So here, both of them should not be 0. Then you can safely conclude that A and B are collinear vectors. So this is a very important test for collinearity, other than the fact that you can also write A as some lambda times B, lambda being not a 0 quantity. Okay, if A is not a null vector, lambda should not be 0. So this is test number 1. This is test number 2. In schools, normally we talk about this. This is generally taught in schools. But this is equally important. You should be knowing it because you may need it for some competitive exams also. So NPS Rajajinagar and NPS Yeshwantpur, have you been taught the concept of collinearity of two vectors in school?
Yes, sir.
They taught about this. They would have just taught about the second test, isn't it?
Yes, sir. Second only.
Second test. Yeah. This test is normally not taught in school because it is connected to the concept of linearly dependent and independent concept, which is beyond your school syllabus. Aditya wants me to go up. Aditya, such a young age, you want me to go up. Which place? Here? Here? Where? I think this is the starting point of the page.
Yes, sir.
Yeah. Venkat. Venkat is saying, sir, you are not young anymore. You are a budhau, sir. See, Aditya is also backing him up. Yes, sir, you are not young, sir. Wait, I'll set the next Kemon test very difficult. No, sir, you are very young. You were born yesterday only, sir. Okay, is this fine? Next theory that is very important is, I'll come to this concept. Before that, I would like to speak a little bit more about. Okay, let's give you the second theory. Okay, then I'll try to come back again. Second theory says a triad of coplanar vectors. What is the meaning of coplanar vectors? That means they can all be brought to a single plane. A triad of coplanar vectors is linearly dependent. Okay. This theory can also be, you can say a corollary could be a triad of non-coplanar vectors is linearly independent. I would like to add a corollary there also. Yeah, what did I say here? A pair of non-collinear vector is linearly independent. So I would like to add over here a pair of linearly dependent vectors. A pair of collinear vectors. Vector word I have missed out, I think. Yeah. A pair of collinear vectors are linearly dependent. Right? Both mean the same thing. Yeah. So let's go back to the second slide. So here basically what I'm trying to say is that if you have three vectors which are on the same plane, let's say there's a vector R, there's a vector A, there is a vector B, which are in the same plane or they are coplanar. Okay. Then basically you can express a linear combination of A and B as your R, right? In other words, if you try to do this, okay, then not all A, M1, M2, M3 will be 0. Other way to look at it is, if let's say M3 is non-zero, then I can write R as negative M1 by M3A, negative M2 by M3B. In other words, I can express R as some scalar times A and some scalar times B. That means XA plus YB. Where this X and Y are scalar quantities and they are unique. Now, what is the meaning of unique? Unique means for a given R, A and B, you will be only getting one pair of X and Y by which you can connect R, A and B. There cannot be several pairs of X and Y by which you can express the same relationship. Let me give you a simple example and let me prove this first. So what is the proof for this? See, it is very simple proof. If let us say you had a vector A, let me draw it in red, and you had a vector B, let me draw it in blue, okay, and there is some vector R. So let's say this is A and there is a vector B and there is some vector R. Let me draw it in yellow. Okay, there is some vector R. Now I have purposely made them co-initial. They did not be co-initial, but what I'm trying to say, they are coplanar. So what does this theory say? This theory says that you may construct a parallelogram in such a way by fiddling with the magnitude or direction of A and B. That means this is what? This is a scalar multiplication of A, right? That means you are trying to play with its magnitude or direction in such a way that you can make two such vectors from A and B whose resultant would be R, which is actually obvious. So let us say I reduce the size of this to this much, okay, and I increase the size of this to this much. So basically I'll be able to create a parallelogram. Sorry, not this much also. I think this much is required only. Okay. So what I'm doing is I made two such vectors XA. This is your XA by scaling up the direction of A over here. In this example, I'm scaling it up. Here in this example, I have to scale the magnitude of B down to YB. And in such a way that a parallelogram will be formed like this, where R will be the resultant of XA and YB. So this is a parallelogram created, and we have seen the parallelogram law of addition. So it implies R will become the resultant, or you can say the sum of these two scalar quantities. And this can be done with any set of three vectors which are coplanar. I'm repeating it. If any triad of vectors are coplanar, you can always make one of them the resultant of some scalar multiple of the other two. So a parallelogram like this can always be created. Are you getting my point? And this parallelogram, while you are creating, then scalars X and Y will be unique. Please get this. Here I'm assuming A and B are non-collinear, right? Because if A and B are non-collinear, you will not be able to complete a parallelogram like this. Are you getting my point? Okay, so here I'm assuming my A and B are non-collinear. We will come to it. We'll come to it, Venkat. Okay.
Okay, sir.
Now, this is something which I proved. What is the proof for that such a combination of X and Y will be unique? See, very simple. Let us say, I'll write it uniqueness proof. Uniqueness proof. Let us say there could be one more possible representation for R as X dash A plus Y dash B. So what I was claiming that this representation of X and Y for that particular R will be unique, right? So now I'm assuming let there be another expression for R. There's an alternative expression for R as X dash A plus Y dash B. Now, since both these expressions are representing the same vector R, we can equate it. Correct? Now watch this very closely because it will say a lot of things. Now, if this is the case, it means X minus X bar A plus Y minus Y bar or Y dash B is equal to a null vector. Now remember, A and B are non-collinear vectors, means since A and B are non-collinear vectors, means they are linearly independent. Correct? Means A and B are linearly independent. Correct? And we have seen that in case of, I'll just write in shortcut in, yeah. And we have seen that in case of two vectors, if they are linearly independent and you are expressing a scalar combination of these as null vector, then it can only result to those two scalar quantities being individually being zero, which means X dash is same as X, Y dash is same as Y. That means this representation is unique. This representation is unique. Okay. Now, I would pause here for some time and try to explain this. When you write a vector in 2D as I and J components, right? So normally when we write a vector, let's say R in 2D as 3I plus 4J. Okay. Remember that it is not necessary that these two vectors that you have chosen over here has to be perpendicular. They have to be non-collinear. Okay, so any vector in 2D space can be expressed as a linear combination of two non-collinear vectors. It needn't be perpendicular vectors. Perpendicular is a special case of non-collinearity. Are you getting my point? It should just be linearly independent of each other. It should just be non-collinear to each other. Are you getting my point? This is an example only, Aditya. When I say you can express R as XA plus YB, so any vector which is in the same plane of I and J, right? Or which is in the same plane of A and B can be expressed as a linear combination of A and B. At that point, you should understand that A and B should be linearly independent or should be non-collinear. I and J are just two special cases which satisfy the same criteria. Okay, so normally when I ask students that is it required to have any 2D vectors in terms of I and J only, or in terms of any two perpendicular directions only, right? Can I not have any two other directions which are not perpendicular? They say no, they have to be perpendicular. Somehow in physics they have learned that you can only resolve vectors in two perpendicular directions. See, we do that because we don't have the component of I in terms of J, but it is not mandatory to do that. You can write any 2D vector as a linear combination of such A and B which are non-collinear to each other. they need not be perpendicular to each other. That is what I'm trying to say. Perpendicularity is a type of non-collinearity. So do not have a very narrow, you can say, understanding of that concept. So my point here is any 2D vector can be expressed as linear combination of two such vectors where these two vectors are non-collinear. That's it. It is not necessary to have I and J only. Are you getting my point? What I'm trying to say here? I and J are just convenient choices for us. Correct? Right? Similarly, we'll talk about when I talk about a system of three vectors. A system of 4 points, etc. So as of now, is this clear? I'm going to move ahead.
Could you go up slightly?
Yeah, sure. This part or this?
The part where you wrote the theorem. The part where you wrote the theorem.
Theorem. Okay, it is this part. Okay. Now coming to.
Yes, sir. Thank you, sir.
What Sai was saying. If there are 4 vectors, okay, let's say there are 4 vectors R, A, B, and C. Okay, these 4 vectors, or more than 3 vectors, to be more precise, more than 3 vectors. More than 3 vectors will always be linearly dependent. Okay, so let us say I have R, A, B, C vector, and let's say A, B, C vectors are non-coplanar. Okay, if they're non-coplanar, then please note there will always exist such scalar quantities M1, M2, M3, etc., where a linear combination of it will imply that not all M1, M2, M3, M4 are 0. So let us say M1 is non-zero, so I can always write R as minus M2 by M1A, okay, plus minus M3 by M1B, plus minus, sorry, yeah, this should be M4, my mistake, yeah, minus M4 by M1C, correct? In other words, I can always write them as this relation. What I'm trying to explain over here is that any vector can be expressed in terms of, note down, any vector can be uniquely expressed as linear combination of 3 non-coplanar vectors. And a typical example of this is your expressing any vector in terms of I, J, and K. So when you write, let's say a vector A to B, 3I plus 4J minus 2K, what are you doing actually? You are trying to express a vector in 3 dimensions as a linear combination of 3 vectors which are linearly independent, or so as to say they are non-coplanar. Are you getting my point? So do not consider that IJK is the only means in which you can express a vector in 3D. No, you can express a vector in 3D, let's say a vector R in 3D, in terms of any linear combination of three such vectors which themselves are non-coplanar. Right? Later on, when we do vector equation, you would realize that I can write any vector like this. Okay, this is a very, you can say, useful methodology to assume an unknown vector. Okay, so any unknown vector in three dimensions can be obtained as XA, YB, ZA cross B, because you know this is not in the plane of A and B. So A, B, and A cross B become non-coplanar. They become non-coplanar, and hence they become linearly independent. Okay, so expressing in IJK is just one specific case where you're using IJK as non-coplanar vector. But in reality, the bigger picture is you can express any vector in 3D as a linear combination of ABC being non-coplanar, or in other words, they are linearly independent. I've already proved this fact that three non-coplanar vectors are always linearly independent, and coplanar vectors are always linearly dependent. Are you getting my point? This is very useful. This will be very much used in vector equations, which we are going to talk about in the last part of vectors. Very useful in solving vector equations. Solving vector equations. Is it clear? Now, how do I justify this? Very simple. See, let us say I have OA. Sorry, I have vector A. I have vector B. Okay, let's say I take the direction of vector B like this. Okay, and I have a vector C like this, let's say. Okay, let's say A and B are on the same plane and C is not in the same plane. Okay, and there is any vector R, let's say. I'm just assuming a vector R to be like this. Let me draw it in another pen. Okay, then what this says is that you can always draw a parallelepiped in such a way. For example, I can always draw a parallelepiped in such a way. I'm sure you would have heard of the name parallelepiped from your school teachers. Have you? This is just a perpendicular dropped from here. Okay. Let me draw it slightly smaller here. I mean, I'll draw it in three dimensions like this. Okay, so let me just re-sketch this. That would be a better sketch than sketching this like this. Yeah. So let us say this is my direction of one vector. This is my direction of another vector. And this is my direction of another vector. Okay. So let's say I call this as my vector A. Let me just complete this. Yeah. Let's say this is my B vector and this is my C vector. Okay. So let's say A, B, C are such vectors. As you can see, I've drawn it in such a way that they are non-coplanar. Then let us say I want to express any vector like this. Let's say this red vector. Okay. So what it is saying that any red vector R can be expressed by suitably scaling up or down A. So let's say this is your XA. Okay. Suitably scaling up or down B. So let's say this part is YB, and suitably scaling up this part. Let's say this part is ZC, such that if you come XA plus YB and go in this direction by ZC, so see how it works. You are coming here by XA, going in this direction by YB, and going up by ZC. Then you are basically reaching from this point to this point, right? So a kind of a closed loop is getting formed. So R can be expressed like this. Okay. So any vector in 3D can be expressed as a linear combination of non-coplanar vectors. And this is a very useful concept which we are going to learn more in detail in the vector equation part of our discussion. Okay. So from the concept, whatever we have studied so far, these things surface out, which is going to be very, very important. Now, let's go back. Yes, Venkat.
So the normal convention of IJK is just a special case of that.
Yes.
Oh,
the normal convention where you try to resolve any 3D vector in terms of IJK is just a special case and nothing else. Is just a special case of representing a vector in terms of or in linear combination of 3 non-coplanar vectors. So any 3 non-coplanar vector will help you to express that vector. IJK is just a convenient choice.
Okay, sir. Okay, sir.
Okay. Now I would like to go back and start this process from the beginning. In this discussion, I will talk to you about 4 things. Number 1, I'll talk about or you can say I will talk about collinearity and non-collinearity conditions. Collinearity and non-collinearity conditions of 2 vectors, which I've done actually, but I'll do it again I'll just write it down at least if I'm not explaining it to you again. Collinearity and non-collinearity of 2 vectors. That's number 1 thing that we will do. Second thing I will talk about is collinearity and non-collinearity of 3 points. Now, one second. Why don't we talk about collinearity and non-collinearity of 2 points?
Always.
They are always collinear. Yeah, so why should we talk about collinearity of 2 points? Okay. Third thing that I'm going to talk about is coplanarity of 3 vectors, which I've already done, but I'll do it again. I'll give you the required resources for that. Now, why don't we talk about coplanarity of 2 vectors?
Yeah, and always they are coplanar.
They are always coplanar. Remember, dear students, I'll write it down. We don't talk about coplanarity of 2 vectors because 2 vectors are always coplanar. This cannot be said for a line, by the way. 2 lines in 3D are not always coplanar. Okay, 2 lines in 3D can be skew lines also. So we'll talk about that when we start 3 dimension with you. And fourth thing that I'm going to talk about is, in fact, coplanarity and non-coplanarity, both we'll talk about. Okay, so the concept is the same. It's just that there are 2 ways of looking at it. So coplanarity and non-coplanarity of 3 vectors. Fourth thing that we'll talk about is coplanarity and non-coplanarity of 4 points. 4 points means 4 position vectors. Okay. Why don't we talk about coplanarity and non-coplanarity of 3 points? Because 3 points are always coplanar. Yes. Now try to imagine this for 1 second. Take 2 points on your table and take 2 points above. You can always draw a triangle. You can say you can always draw a 2-dimensional triangle connecting them. Okay. So 3 points are always coplanar, just like 2 vectors are always coplanar. So we don't discuss about those. So these are the 4 things primarily we'll be discussing in the next half an hour or so. Now pay attention, these concepts are not done in school, and hence There are a lot of misunderstandings and myths that is associated with these concepts. Let us talk about the first thing, collinearity / non-collinearity of two vectors. I'm speaking and writing something else. And non-collinearity of two vectors. Okay, so two non-zero vectors A and B, two non-zero vectors A and B are said to be collinear, as I've already discussed with you, if one can be expressed as a linear combination of the other. One can be expressed as a scalar times the other. Right? This is the most simplest way to figure out whether two vectors are collinear or not. Otherwise, if you express a linear combination of A and B as null, it should lead to X being and Y being non-zero each. Okay, so the reverse is, if they are non-collinear, then A cannot be expressed as a linear as a scalar multiple of B. Now, what is the meaning of this? So many people ask me, sir, what do you mean by they cannot be expressed as a scalar multiple of the other? I'll take an example. Okay, we all know I plus J and I, they are non-collinear. Correct? No. I'm just taking an example of two such vectors which you know they are non-collinear, right? You know they are not parallel, right? I plus J and I are not parallel, isn't it? Now try to do this. Try to express I plus J as lambda times I, right? See what will happen. Since there is no J, let me write 0J. Correct? So if you bring it to one side, it will become something like this. Correct? Now, you know I and J are linearly independent vectors. That means their coefficient should be individually be 0 if you are trying to get a null vector. But this coefficient is 1. 1 is not equal to 0. That means even if you try to equate the coefficient of I to I or J to J, now you understood why we used to compare coefficient of I with I and J with J. It is because they were linearly independent, because they were non-collinear, right? That was the hidden story which nobody told you. You just compared it blindly, right? like we always do. But the reason behind comparing I with I and J with J is not very obvious thing. It is because I and J were linearly independent, or you can say non-collinear, and hence by the non-collinearity theorem their coefficient should individually be 0, right? And that's why you used to compare the coefficients. So here also, if you try to compare, you will get lambda as 1, but you will get 1 as 0, which is not possible. Are you getting my point? Or let us say, I take another case. Let's say I minus J and I plus J. You know they are non-collinear, correct? Now try to do this. I minus J is some lambda times I plus J, right? So if you compare the coefficients, which is very much legal to do because you know I and J are non-collinear, then you'll get lambda as 1 and you get lambda as minus 1 also. That means there will be inconsistency in the value. So somewhere something will go wrong when you do this comparison, right? So when you do this comparison, or you do this equation of one as scalar times the other, you would realize that something wrong will happen in that equation. Either an inconsistency will happen or something like non-mathematical thing will surface out. So you will not be able to express one as a linear combination type the other. As a scalar time the other. Why I'm saying linear combination. And if you try to express one as a linear combination as a null vector, so if you try to express a linear combination of A and B as a null vector, then this will only lead to X and Y both being 0. That is the check normally we do if you want to know whether two vectors are collinear or non-collinear. However, in our school, and what is recommended by most of the teachers is this method. This method is good to know, but normally we don't use it. Okay, now people ask me, sir, can you use this to show that these vectors are non-collinear? Yes, see what will happen. You know they are non-collinear, right? So if you do X times 1 plus Y times the other and try to equate it to null, you would realize that the only solution you will get is X is 0, Y is 0. Let's check. Does it come out like that? So if you collect your I coefficients, it will be X plus Y. Collect your J coefficients, it will be minus X plus Y, correct? Yes. Now since I and J are non-collinear vectors, you have to get these two as 0. That means this and this should be 0. This can only lead to only 0, 0 values. So basically you will only get X as 0 and Y as 0 by solving these two equations. And hence these two vectors that you had were non-collinear vectors. So lambda approach and XY approach both are clear. Please note this down. I discussed this partially in the beginning, but I wanted you to have a one-stop discussion for all these things. So first part is clear. Second thing that I'm going to discuss is collinearity of 3 points. Collinearity slash non-collinearity of 3 points or 3 position vectors. Can I move to the next slide? Can I move to the next slide?
Just a second, sir, please.
Okay.
Done, sir. Thank you, sir.
So now let's talk about collinearity, and at the same time I'll also refer to non-collinearity conditions also. Collinearity or non-collinearity of 3 points, but you can read it as position vectors. Points are position vectors only. Okay, so there's no difference. Point of coordinate geometry is like position vectors in vectors. Okay, so let's say you have 3 points, A, let me name it as capital A, B, let me name it as capital B, and C. So small a, small b, small c are position vectors of A, B, and C. Okay. Now, how will I test whether these 3 points are collinear? Now, if you see, if you connect any 2 vectors, let's say I connect A to B, AB vector, and I connect A to C, I'll make a yellow line. So can I say if A, B, C are collinear, it will automatically imply that any 2 vectors made out of it. I'm just taking an example. Let me write for example. Okay, will be collinear. Okay, so if 3 points are collinear, then take any 2 vectors made up of those 3 points, whether you take AB, BC or you take AC, BC, right? Any 2 vectors you make out of those 3 points, they will also be collinear. Do you agree to this or not? Yes or no? Correct. So what have I done? Yes, of course, the area thing will come into picture. I'll talk about it. That is connected to cross product. Okay. So what I'm trying to do here is I'm trying to convert the concept of collinearity of 3 points in terms of collinearity of 2 vectors, because I already know them. In my last slide, I already discussed about it. Yes or no? Correct. So if such is the case, then I can always check for whether, let's say AB is B minus A, we all know that, whether I can express this as some scalar times AC or any combination. I'm not denying that you have to take AB and AC, you can take any combination you want. Okay. So whether you can express it like this, where lambda is some scalar. If you're able to do this, then basically you can say that these 3 points are collinear. And let me tell you, you can do any combination. Don't get me wrong, I'm not trying to say that you have to write AB as lambda times AC only, right? You can do AC as lambda times BC or AB as lambda times BC, any combination you want to take up. Okay, is it fine? Any questions, any concerns here? Okay, now this is for collinearity. And if your points A, B, C are non-collinear, then opposite thing will happen. Opposite thing will happen means you will not be able to express one vector as a scalar times the other vector which you have made from those 2 points. Okay, so please make a note. This is method number 1 to check collinearity or non-collinearity of 3 points. This is method number 1. Method number 2 says if A, B, C are collinear, okay, then a linear combination of this expressed as a null vector would imply that x plus y plus z is 0, but all x, y, z are not 0. That means despite all of them not being 0, their sum will be 0. This is a slightly tricky way. But what is the core principle behind this particular concept? Now see here, it is basically hinting to the fact that if 3 points are collinear, then one must divide the join of the other in the ratio something, right? So there has to be a division happening, correct? So if a division is happening, you can write C as MB plus NA by M plus N, correct? In other words, if you restructure it, it will be M plus NC equal to MB plus NA. Further, if you restructure it, you'll see NA plus MB minus M plus NC equal to a null vector, correct? That means, now try to compare this with this. So let's say this is your X, this is your Y, and this whole thing is your Z. So what you're seeing over here is that a linear combination of A, B, C expressed as a null vector would imply X plus Y plus Z, which is actually N plus M minus M plus N, will give you a 0, despite all of them not being 0. Are you getting this fact? So this is you can say a more difficult way to figure out whether the 3 vectors are collinear or not. So again, I'll repeat, 3 points with position vector A, B, C are collinear when, if you try to express a linear combination of them as a null vector, then the coefficient of x, a, b, c will add up to 0 despite all of them not being 0. Are you getting my point here? Okay, this is the second way to prove the collinearity of 3 points. My bad. Collinearity of 3 points. Right?
Sorry?
If they are satisfying the fact that it is 0 because all of them are 0, then they would not be collinear. On the contrary. Yes, Tripan was asking something.
So that will be similar to that. I was going to ask, what if one of them is 0?
If one of them is 0 and the other two are not 0, that is fine. But not all of them should be 0. It cannot happen that two of them are 0, because then third one will automatically be 0. Then in that case, what will happen? It will be a system of, or they will be non-collinear.
Sir, but then if we take C as 0, then we'll get in this thing that you did, we'll get NA plus MB is equal to 0, which means that, which just gives us that A and B are collinear. That's it.
Come again.
Sorry, A and B are, yes, sir, A and B are collinear. Okay, that will give us that it's in the same line as the.
Yes. Is this
and
clear?
Sir, can we say that 0 vector is collinear with any vector?
0 vector does, yeah, you can say that. I mean, that is fine. 0 vectors can be said to be collinear to any vector. Yeah.
Okay.
Yeah, that is an obvious statement. Okay. Is this fine? So we had discussed about collinearity and non-collinearity of 3 points. Now I'm going to the concept of coplanarity. That is our third discussion as per our chart. Now I'm going to talk about coplanarity or non-coplanarity conditions for 3 vectors. As I had already discussed, we don't talk about 2 vectors non-coplanarity because they are always coplanar. So this is something which I've already discussed with you. If 3 vectors are, if vectors A, B, C are coplanar, that means one of them can be expressed as a linear combination of the other two. Okay. Or you can say that if you want to write a linear combination of these 3 vectors to be a null vector, then M1, M2, M3, not all are 0. M1, M2, M3 are all not 0. Is this fine? Now this concept has been converted to determinants. See how. If A, B, C are coplanar, you can always write one of them as a linear combination of the other two, right? Okay. This we had already discussed through this one only, correct? Now what I'm going to do is I'm going to write A as A1I, A2J, A3K. Let us say A has been given to me in a resolved format like this. B has been given to me as B1I, B2J, B3K. And let's say C has been given to me as C1I, C2J, C3K. Okay. Now, if I make a determinant out of these coefficients of I, J, K for these 3 vectors, and if they happen to be, coplanar, so if these 3 vectors will happen to be coplanar, then you know what will happen to this determinant? Then this determinant would be 0. Why? Why will it be 0?
It's like the area of that.
No. See, understand from here. See what you're trying to say. You're trying to say that C1, I, C2J, C3K is X times A1I, A2J, A3K plus Y times B1I, B2J, B3K. Correct? In other words, since you know I, J, K are non-coplanar and hence linearly independent, your coefficient of I will be compared to this. Correct? Your coefficient of J will be compared to the coefficient of J on the other side. and your coefficient of k will be compared to the coefficient of k on the other side. In other words, if you do this operation, R3 as x times R1 minus y times R2, what will happen in this determinant? You will end up saying something like this. C1 minus XA1, oh sorry, I have to have more space, so I'll just write them slightly far apart. Let's say A2, B2, A3, B3. Yeah, so you'll have C1 minus XA1 minus YB1, and here you'll have C2 minus XA2 minus YB2, and here you'll have C3 minus XA3 minus YB3. And what is the value of C1 minus XA1 minus YB1? They're 0. So this guy will be a 0, this guy will be a 0, this guy will be a 0. As a result, the whole row number 3 will vanish. And as a result, this is going to be 0. Which I'm sure you would have learned in your school as the scalar triple product of A, B, C will become 0. This is called the scalar triple product. Have you done scalar triple product in school?
No, sir.
Oh, then you'll not understand this. Okay, ignore this. We'll talk about it later. Okay. So many people, when they are asked this question, are these three vectors coplanar? Then they take this approach and check whether the determinant coming out from here will be 0 or not. Now this determinant is actually not the area, it is the volume of the parallelepiped, which will be made by A, B, C as the coterminous edges. Again, this is something which we'll learn later on. Don't worry about it right now. Just understand that this condition has led to this determinant being 0. That's it. How? I have already explained you. Is that fine? So, if this determinant doesn't become 0, or if you are unable to express one vector as xa plus yb uniquely, then you have to admit that those three vectors were non-coplanar. Okay, now what do I mean by expressing it as not able to express it as this? Let's say I'll take a very simple example. Very simple example. Let's say, in fact, I'll take it in the form of a question. Yeah. Are these three vectors coplanar or not? So let me give you the vectors. Minus 2i, minus 2j, plus 4k. And let's say minus 2i, plus 4j, minus 2k. And 4i, minus 2j, plus 3k. Okay. Now I'll show you both the ways. I'll show you the determinant way also, and I'll show you this way also. Okay. So let me show you the first way first. So what do? I take any one of the vectors and try to express it as a linear combination of the other two. Now, it doesn't mean that I have written C as XA plus YB, then you'll always go for, whichever is the last one as a linear combination of the other two. You can take in any fashion you want. So let me do one thing. Let me write A as a linear combination of B and C. Okay. Now see what will happen in this case. Compare the I coefficients on both the sides. Now this is not something which I've already explained you why we can compare it, because I, J, K are all linearly independent of each other. So if you bring it to one side and collect I coefficients, J coefficients and K coefficients and compare it to null vector, they will anyways be 0, 0, 0 each. So you can directly compare the coefficients over here. So minus 2 will be minus 2x plus 4y. Similarly, minus 2 would be 4x minus 2y. And 4 would be equal to minus 2x plus 3y. Now try to understand over here. You would be feeling that I have only two unknowns and I have got three equations. So one of the equation is a waste. No, the other equation is basically a checkpoint for you that the answer that you get from the first two should satisfy the third one. Let us check, is it happening like that? So let us solve here. Let me multiply this with a 2. Let me multiply this with a 2 and add them. So if you multiply 2 with the second equation and add them, you'll get a -6. Okay. Here you will end up getting 8 minus 2x, which is 6x. So x is going to be -1. Correct? Y is going to be -1 only. Correct? X is -1, y is also -1. Does it satisfy the third one? Check it out. So -2 into -1 plus 3 into -1. Does it give you 4? No, my dear, it doesn't give you 4. Are you getting my point? So when such a thing happens, what do you conclude? What is your conclusion? What is your conclusion?
Non-coplanar.
Yes, A, B, C are non-coplanar, or they are not coplanar. Correct? Right? A similar thing can also be done through the use of determinants. Now let us use this and see whether I am getting 0 or not. So determinant method, where should I write? Yeah, determinant method. Determinant method. This is the most favorite one of all students because it takes hardly any time. You just find out the determinant. So you don't have to solve equations like you do over here. So let me write the coefficient. -2, -2, 4. -2, -2, 4. -2, 4, -2. -2, 4, -2. 4 -2, 3. Let me expand this. So let me expand with respect to the first row. So -2, 12, -4 is 8, then +2, -6 plus 8 is 2, correct? And +4, 4 minus 16 is -12. Okay, I can say here for with surety that this is not going to be 0. Okay, and straight away you figure out if your determinant is not 0 means your A, B, C are non-coplanar. I'm sure out of the two methods you like the second one a lot because it's too simple. You can directly use a determinant. But don't forget, this concept has come as a analysis of this particular method. Okay, and this method has come from the fact that if 3 vectors are coplanar, you can always make a suitable parallelogram from A and B whose resultant would be C. Got the point? This is the basis of all the things that we are going to learn. So now, without much waste of time, by the way, similarly figure out the conditions for, the conditions for non-coplanarity. So the condition for non-coplanarity is you will not be able to express this uniquely. Uniquely means one set of values will not match with the other. So there will be an inconsistency in the value of x and y. Okay. Second thing is that the determinant which you made by the coefficients, ijk coefficients of these vectors, they will not give you a determinant value as 0. Okay. So these are the two things that we need to keep in mind. Next, fourth thing that we had in our to-do list was coplanarity / non-coplanarity of 4 points. Read it as 4 position vectors. Okay. Now here the approach is pretty simple. If you are been given, let's say, 4 points like this, A, B, C, D, where A has position vector of small a, B has position vector of small b, C has position vector of small c, and D has position vector of small d. Now this is very clear in our mind that if A, B, C, D are coplanar, if they are coplanar, then do you realize that even any three vectors made out of it, let us say AB, AC, AD. I'm just taking an example. For example, even these three vectors would be coplanar. Yes or no? Do you agree with me on that or not? So if I make any three vectors out of it, let's say AB vector, AC vector, and AD vector, then can I not say AB, AC, AD are coplanar if these points are coplanar? Are you getting my point? Let us say C was not in the plane of ABD. Let's say it was slightly higher. Correct. So let's say the situation was like this. A was here, B was here, D was here, but C was slightly higher over here. Then you'll automatically realize that AB, AC, and AD will not be in the same plane. Right? So automatically they will become non-coplanar if A, B, C, D were not coplanar, or any one of them was not coplanar to the other. Are you getting my point here? So this condition boils down to the fact that if you want to check whether 4 points are coplanar, you just have to make any three vectors out of those 4 points. Now again, I'm repeating, any three vectors you can make. You can make AB, BC, CD also. Not an issue. You can make AB, AC, BD also. Any three vector, Baba. Any three vector. Okay. 6 vector combinations can be formed, right? Okay. So any three vector you can make from this, and if you're able to prove that one of them can be expressed as a scalar, or you can say a linear combination of the other two, or you can say the determinants formed by the IJK coefficients of these three vectors you have formed from those 3 points are 0, then basically you can say that even the 4 points A, B, C, D will be coplanar. Are you getting my point here? This is one way. I'll add over here, do this or you do the determinant way. Any way is fine with. Nobody is going to ask you which way you did. Okay. Now this is another way. Let me write it as approach A, and there's an approach B. This is slightly deep. In fact, I would ask you to think about it. If 4 points are coplanar, okay, if 4 points are coplanar and you connect any two of them, let us say this is A, this is B, this is C, and this is D. If I connect these two, okay, and I connect these two, Ajaf, let me not give you a hint. If these 4 points are coplanar, let me name their position vectors like this. If A, B, C, D are coplanar, then there exists scalars x, y, z, w such that a linear combination of these 4 vectors A, B, C, D expressed as a null vector would imply that x plus y plus z plus w is equal to 0, but sum of no 2 is 0. Sum of no 2 scalar quantities is 0. This is a slightly complicated way. Can you tell me why? I was about to prove that, but I thought I would ask you to think about it. Why this would mean this, or why the combination of these two would prove that A, B, C, D are coplanar. So let's say my question to you is, let's say if this is true and this is true, of course, subject to the fact that sum of node 2 is 0, and there's a reason for this also, then why would A, B, C, D be where A, B, C, D point would be coplanar points? Can somebody give me a justification? And what does X, Y, Z, and W actually represent? It's a slightly deep thinking, but I would like you to really stress on your mind and try to figure out what is probably the reason for this to happen. What is the reason for this to happen? Anybody? Okay. So the reason for this to happen is, if A, B, C, D are coplanar, and I connect, let's say, A to B and C to D, okay, or if I connect any two of them, then they would either intersect each other internally or externally. So there has to be an intersection happening. First of all, you have to agree to this. If there are 4 points which are coplanar, and if you connect two pairs, let's say A to B and C to D, they will either intersect each other internally or externally. Yes or no? Because without agreeing to this, we cannot proceed further.
Sir, if they're parallel, you connect A, D, B, C and they're parallel?
I mean, take such a combination which will intersect.
Oh, okay.
Okay. Now here, if they intersect, let's say this ratio be X is to Y. Okay, now you're slowly realizing where I'm going towards. And let's say this ratio is W is to Z. Correct? Now, if let's say I talk to you, what is the position vector of P? What is the position vector of P? Position vector of P. Looking at A and B, you will say it's very simple. It is going to be XA plus YB by X plus Y. Correct? Yes or no? Right? Can I say the same thing can be obtained if I look at C and D and I say it is WC, or you can say WC ZD by, I think I have taken ZC and W, right? So Z should be here. Just for the sake of matching it with our formula. It's no hard and fast rule, whatever you want to call as W and Z. So Z is here, W is here. Yeah. So if you see this, it will be ZC plus WD by Z plus W. Okay. Now, sum of any two should not be 0. It is because of the fact that you don't want the denominators to vanish. Okay. Now, this condition will only hold true when you have these two coming simultaneously. This and this happening simultaneously. How? Let's see. So this will tell me that XA plus YB will be equal to minus ZC plus WD. And from here I can say X plus Y is equal to minus Z plus W. Divide one by the other. If you divide one by the other, what do I get? I get XA plus YB by X plus Y equal to ZC plus WD by Z plus W. Correct? So this condition basically is supported by these two facts, and hence these two facts are supported. So this condition will result only when we have these two conditions getting satisfied. In other words, when these two conditions get satisfied, the points A, B, C, D will become coplanar. This is a difficult way to prove the coplanarity of 4 points, but nevertheless, I have seen questions framed on this as well. So not knowing this should not be in your options. Oh, just because sir told that no, this is an alternative way and I am finding this to be difficult, let us stick to this way. This seems to be very easy. We just have to make 3 vectors out of those 4 points and find the determinant and see whether it is 0 or not. That is fine. That is always there. That's a working rule. I'm not denying it. But be aware of this method also, that if A, B, C, D, whose position vectors are given to you, if they are coplanar, then there would exist such scalar quantity where if you equate it to a null vector like this, then the sum of all of them should be 0 despite the sum of 2 not being 0. Is this fine?
So could you repeat the last part?
Which part?
So where you got those 2 equations?
Yeah, so basically what I'm trying to say is that if this condition and this condition are true, it will lead to this condition, because I can write this like this and I can write this like this. And if I divide these two, this will become the same as this, which is actually a true condition, because you know that if points are coplanar, the join of any two would get intersected at some point. Are you getting my point? So these two lead to this. That's what I'm trying to say, Tripan. And this is true fact. So if this is true fact, that means the truth of these two is also established, isn't it?
So, but then that doesn't mean that the one fact leads to the other two, no, sir?
No. I'm saying that if these two conditions are satisfied, then this condition is obvious from there. And if this condition is obvious, means A, B, C, D points are coplanar. That's what I'm trying to say.
Okay.
Let us take questions, because questions are the right way to go more deeper into these concepts. So let's start with some problem solving. Okay, let's take up some questions. Yeah. If vectors 2i plus 3j, 5i plus 6j, 8i plus lambda j have their initial points at 1, 1, find the value of lambda so that these vectors terminate on one straight line.
Sir,
Yes.
so how can 2i plus 3j have a point 1, 1? It doesn't even lie on that, no?
Which one?
So how can 2i and 3j have initial point 1, 1?
You didn't understand the question. See, there's a vector which is 2i plus 3j. Okay, this is the vector. Okay, and its initial point is I plus j. That means the position vector of this point is I plus j, or 1, 1, what you're calling it. Okay, there's another vector. Let me draw it in blue, which is given as 5i plus 6j, having the same initial point 1, 1. And there's another vector, let's say a red one, like this. Not red one. I think red one is already used up. We'll take gray one. Okay, which is 8i plus lambda j. Right? What should be the lambda that they all terminate on the same vector? That means the ending point of these three will be the same straight line.
Sir, you have to increment, like it will become 3i plus 4j, then like that only, no, sir.
Right. So basically, they are trying to ask what is the what is the lambda value such that the end points of these 4 vectors. This is the initial point. There is some end point also, right? Terminal point. The terminal point of these 3 vectors are on the same straight line.
Oh, okay, sir. Okay.
Let's say this point is A, B, C, such that A, B, C become collinear. That is what they are trying to ask you. Correct?
Okay,
Or
sir.
in other words, they're trying to ask you such that one of the vectors becomes a scalar times the other. I will not use lambda because lambda is already used. Let me use, let's say, delta or something. Once you're done, put your response on the chat.
Sir,
Yes, Anjali.
so I didn't understand how like the vectors can lie on like such a point. Like, shouldn't it lie on some multiple of the
No.
A I cap and B J
Okay.
cap?
See, question is very simple. Question is there are three vectors. Let me name them as, let's say this starting point is D. So DA, DB, DC are three vectors and all of them are starting from D only, and D is 1, 1. So they all have their initial point at D. Okay. So what should be the length? There should be some, they have different lengths. Okay. Their lengths are such that the endpoints all terminate on the same line. That is the question. Now got it, Anjali?
Sorry.
The question is there are three vectors, all of them starting from an initial point 1, 1, but
Yes,
they
sir,
terminate
that's my
on
doubt. Like, how can they all start from the same point?
the,
Like, don't they have different direct? Oh, okay, okay.
starting point can be brought to be the same.
Yes, sir. Yes, yes, yes.
Okay, the answer is yes, correct. Somebody said, Aditya is correct. No, Siddharth, that's not correct. See, very simple. What is AB vector? If I ask you a simple question, what is AB vector? You can use a lot of things. You
DA
can,
minus DB.
you can take DA, right? And see, if you want to go from A to B, what path you can choose? I can go from A to D and I can go from D to B. Correct. So I can say AB vector is nothing but minus 2i minus 3j plus 8i plus lambda j. Correct. This is my AB vector. What is BC vector? So if I want to go from B to C, let me put a yellow direction. Can I not go from B to D and D to C? Because I know these two vectors. Correct. So B to D, if I'm going in minus 8i minus lambda j direction, opposite to this. And D to C will be 5i plus 6j. Right. Now, put all your I, j terms together. So this will give you 6i and this will give you lambda minus 3j equal to some delta times. Here also you'll have minus 3i plus 6 minus lambda j. Now, compare the coefficient. So 6 will be equal to minus 3 delta and lambda minus 3 will be delta 6 minus lambda. From here I can say delta value comes out to be minus 2. So lambda minus 3 is minus 2 times 6 minus lambda. So this clearly gives you lambda minus 3 is equal to minus 12 plus 2 lambda. So lambda value is 9. Clear? Any questions?
No, sir.
This was easy. You should have all got it. Next.
Sir,
Yes, Tripan.
sir, I had another doubt in that x plus y plus z plus w derivation.
Yeah, tell me.
Sir, what will happen over there if x plus y becomes 0?
See, it is not that I'm just claiming x plus y should be 0. The combination of no two should be 0, because then this division will not be a valid one. What are you doing? You are writing two terms to the left side of the equation, two terms on the right side of the equation. Correct. If any one combination becomes 0 and you are dividing it, then basically that division will be null and void.
Yes, sir, that's fine. But then, like, physically, what will it mean?
Physically, what will happen? That means you have chosen two such lines which are never meeting at all.
Okay, sir.
Sir, but B position vector and A position vector won't be there only, no?
Why?
If x plus y equal to 0, sorry, I took x and y equal to 0.
Got it, sir.
Let's solve this question. A, B, C are three non-zero vectors, no two of which are collinear. And A plus 2B is collinear with C. And B plus 3C is collinear with A. Then find the value of A plus 2B plus 6C. Correct, Siddharth. Very good. Correct, Ayush. Correct, Aditya. Okay, see, most of you have solved it correctly. If A plus 2B is collinear to C, can I say A plus 2B can be expressed as lambda C? Okay. B plus 3C is collinear to A, so can I say it can be expressed as mu A? Correct. Now, can I say from the first equation that yeah, I have to get A plus 2B plus 6C kind of an expression. So what I'm going to do is I'm going to eliminate B from it. So from here I can say 2B is equal to lambda C minus A. And from here I can say B is going to be mu A minus 3C. In other words, 2B is going to be 2 mu A minus 6C. Okay, compare these two. So lambda C minus A is equal to 2 mu A minus 6C. In other words, 2 mu plus 1A equal to lambda plus 6C. Correct? Now, please be informed that A and C are non-collinear. If A and C are non-collinear and you are trying to get a linear combination of this, or you can say you're trying to do something like XA equal to YC kind of a thing, then X and Y both individually should be 0. Correct? So this will imply that 2 mu plus 1 should be 0. That means mu is negative half and lambda should be negative 6. If lambda is negative 6, then directly your job is done, because from here you figure out that this is negative 6C. And if you figure out that this is negative 6C, means your A plus 2B plus 6C is going to be a null vector. For a null vector, the modulus is always going to be a 0. So this answer is 0. Is that clear?
So here that mod means that normal magnitude only, no sir? That
Magnitude.
x square plus y
Magnitude.
square and all.
Mod means magnitude, yes.
Okay, sir. Okay.
A and B are two non-collinear vectors. Show that these 3 points are collinear if this determinant is equal to 0. Don't get confused. The determinant thing that we had used was for coplanarity of 3 vectors. Here they are asking about the 3 points being collinear. This determinant should be 0. Don't confuse it with that. If anybody is done, just type done. Okay, see here, everybody. Here the second method that we had discussed, and I told you that it is not very preferred method, that is going to help you out. We had learned that any 3 points, let's say PQR, or any 3 position vectors PQR are collinear when you have a linear combination of this x plus to a null vector will lead to x plus y plus z being 0, but not all 0. Correct? Do you remember this? Please recall this. This was the second method to prove. One method was if you make any 2 vectors with these 3 points, you try to make any 2 vectors with these 3 points and show that those 2 vectors are collinear. Okay. Another method which was not that preferred, but I told you some questions can be framed on that, is where you take a linear combination of those 3 points, express it as a null vector, would lead to x plus y plus z being 0, not all 0. Okay. Now, how will this help us to solve this question? Now, let us see. So this is your, let's say, P. This is your P. This is your Q. And this is your R. Okay. So when you write it like this, you're going to write X L1A M1B, Y L2A M2B, Z L3A M3B equal to null. Correct? Yes or no? Now, if you collect all your A coefficients, what do you get? You get X L1, Y L2, Z L3A plus M1X, M2Y, M3Z B equal to null. Now it has been specified in the question that A and B are non-collinear vectors, means they are linearly independent. If they're linearly independent and you're trying to express a linear combination of 2 linearly independent vectors as a null vector, that would ultimately lead to these coefficients being 0 individually. Let me write in the same fashion as I've written on the top. Okay. Not to forget that you have one more condition, that x plus y plus z should be 0 also. Now, this is a system of homogeneous equations with non-trivial solutions.
The determinants thingy.
Correct? Why non-trivial solution? Because as I told you, not all 0. That means x, y, z are not all 0. If it is 0, then that would lead to a trivial solution, isn't it? And when a system of homogeneous equation has a non-trivial solution, what do you comment about the determinant of their coefficients? Yes, yes, tell me. 0 or non-zero? 0 or non-zero?
0.
0.
0. Isn't this what they had asked you to prove? Let's go up. Yeah, hence proved. See where it got connected. It got connected to your determinants chapter. Okay.
Sir.
Yes, sir.
Sir, could we also prove that now taking L1, L2, L1, M1, L2, M2, L3, M3 as 3 points, and then could we prove that they lie in one line? That is, you visualize 2 random vectors, you make them up and down, here, like expand them, contract them, whatever.
See, Venkat, if your A, B were I and J, it is just like 3 coordinates were given. You are given x1, y1, x2, y2, x3, y3. 3 coordinates of points are given. The area is 0.
Yes,
so
sir, that's what.
You can connect it to area, but in order to substantiate that, somebody should say this is I and this is J. But here they're giving you a non-collinear case. I and J are special types of non-collinear case. I agree with that. But if you're trying to equate it to area of a triangle, then you should be able to say A and B are your I and J. Okay.
Oh, okay, sir.
So
Okay.
that case is a subset of this case.
Okay, sir. Okay.
So this is I've used a broader way to prove it. If I wanted, I would say, okay, take A as I and B as J. This is the expression for the area of a 2D triangle. And since they are collinear, The triangle should collapse, give you 0, and hence the answer is 0. That is anyways there for me. But I just wanted to take a broader approach than assuming A and B as I and J respectively.
Understood, sir. Understood.
Okay, let's take this one. Yes. Any success, anybody? Okay, now let's solve this. Can I
One
say,
second.
yeah. Can I say these three vectors are coplanar? They should be 0. Yeah, of course they're symmetric matrices. How does it help, Venkat?
That's what I was thinking.
Actually, not exactly symmetric because, yeah, I think yes, they're symmetric. Now see, just if you stress more on your this thing, you would realize that I can actually break this as a product of two matrices, two determinants actually. Let's check how. Since there's a 1, I can write, let's say, cos alpha, sine alpha, cos alpha, sine alpha, and there has to be, let's say, 0. So this 1 will be created, and I can keep cos beta and sine beta over here. So now see what I'm trying to generate. Okay, let's say I have this. If I multiply this with the first row over here, I get cos square alpha plus sin square alpha, which is this one. If I multiply this with the second row over here, I get cos alpha cos beta plus sin alpha sin beta, which is actually cos alpha minus beta or beta minus alpha. And similarly, you can write cos gamma sin gamma. Okay, now let's check. What should I keep over here? I can keep anything I want to, but because there's a 0 over here. But let's try to complete others. Similarly, here I have cos alpha cos beta, so I would need cos beta sin beta over here. Okay, and let's say I keep a 0 over here. Okay, so this into this will give me the first element. This into the second will give me 1. This into this will give me this element. Similarly, this can be written as cos gamma sin gamma. Okay, so this into this will give me this element. This into this will give me this element. And I now want this into the last one to give me an A. Now remember, this and this will give you cos square. This and this will give you sin square. So I have to have A minus 1 and 1 over here. Can I say this? Can I justify that this particular determinant can be expressed as a product of these two determinants? Check, verify, then only we'll move forward.
So 1 minute.
Sure, take your time. Why A minus 1? That is clear, right? Because this will give you cos square sin square, which is 1 itself, and this will give you A minus 1. So 1 plus A minus 1 will only give you an A, right? That's why A minus 1 over here. Okay. Now this determinant, if you try to expand with respect to the third column, you will get cos alpha sin beta minus sin alpha cos beta, which is actually sine of beta minus alpha. Correct. This determinant, that is the first one, will give you A minus 1. Same thing, sine beta minus alpha. Correct. Now, it is clearly given to us that the angles are all different angles. Right. That means they indirectly they want to say that this cannot be 0 and this cannot be 0. Okay. Ideally, if they are different also and their difference is a multiple of pi, they should have got a 0. That means they're trying to say A minus 1 can be 0. That means A is 1, which is independent of alpha, beta, gamma. This is not a very well framed question, but this is probably what they intended. Show that A is a multiple of, A is independent of alpha, beta, gamma. Because somebody can argue that even if alpha and beta are not equal, sine of alpha minus beta could be a multiple of pi. So alpha minus beta could be a multiple of pi, and hence this result could have been 0. So they could have framed it in a better way, that the difference of no two angle is a multiple of pi also, like that. Is that fine? Any questions? Other than the fact that it is a poorly framed question. Let's move on to the next. A, B, C, D are 4 position vectors and are related to each other in this way. Okay. I'm sure when you read this, it will sound familiar to you. Isn't it? This line holds the key to everything. What does it mean? Indirectly, what are they trying to comment about the 4 points?
Coplanar.
Yeah. Now see how they have framed the question. They are expecting that a student doesn't know this. Okay. So if let's say you are aware of this concept, then you can directly talk business over here. You can say, okay, yes, that means these 4 guys are coplanar. Now try to see what they are trying to ask you. Prove that if A, B, C, D are concyclic, then mod xy times mod of A minus B is mod, A minus B whole square is mod WZ times mod C minus D square. See, let's be clear about our indications. See, X, A, Y, B, Z, C, and W, D. What did I discuss with you about X, Y, Z, and W in these cases? Didn't we discuss that if let's say this is your A vector, okay, and this is your B vector, and let's say this is your C vector, and this is your D vector, and if I connect A to B, and C to D, then this ratio is X is to Y, and this ratio is Z is to W. Correct? Yes or no? I'm not claiming that this is center. Center may be somewhere over here. Okay. I'm not claiming that this point of meeting is the center. I'm just saying these are like 2 chords which are intersecting each other. Correct? Now, proceed further. How does this lead to this situation? There is one special law in circle which this condition actually speaks. I want to see whether you're able to figure that out. Done? Not Ptolemy, it is the secant law. Okay, now those who don't remember the secant law, let me remind it for you. In any triangle, in any circle, if you take any 2 chords, let's say this and this, okay, let's say A, B, C, D, and they meet at P, then please note PA into PB will be equal to PC into PD. This is called the secant law. Correct? Now do you recall this law? So PA into PB. Now what is PA? Can I say PA will be y by x plus y times AB or BA, whatever you want to call it. So can I say this is your PA? See, whole vector is what? Whole vector, let's say I BA vector. What is BA vector? BA vector will be A minus B. Okay, so mod BA will be mod B minus A, mod of A minus B. And this part is just y by x plus y times the whole thing, right? So this will be the length of PA vector, which is actually PA. Correct? So this part is y by x plus y, the whole length. That is what I have written. Similarly, PB will be what? PB will be x by, now once again I should always put a mod over here because never know, you get a negative answer. Correct? This is your PB. Similarly, what is PC? PC will be W by W plus Z mod. Okay, and the whole thing is mod C minus D. So this length CD is mod C minus D. So the length of this will be mod C minus D. And this is W by W plus Z. W by W plus Z times CD. Similarly, PD will be mod Z by W plus Z. Correct? Now, if you simplify this, it would lead to mod xy by mod x plus y the whole square, mod a minus b the whole square, and on the right side will give you mod wz by mod w plus z whole square, c minus d the whole square. Correct? Now in my answer there is no x plus y and w plus z over here, as you can see. Now ideally they should not be there because we also know from the fact that x plus y is minus w plus z because of this condition. X plus y is negative w plus z, which clearly means mod x plus y is mod w plus z, which means mod x plus y square is mod w plus z square, and that's why these two gets cancelled, and this leads to the final result, right? So this concept is linked to that part which many people would ignore because they will find it relatively difficult, and it is here where you will score a brownie points. Which ratio?
So that I didn't understand that y by x plus y.
See, there's a length which is 10, okay, and there is a point which divides in the ratio 1:2. Then what is this length?
Oh, okay.
1 by 1 plus 2 times 10, you will say, no?
Yes, sir. Yes, sir. Yes,
Same
sir.
thing I did over here. This whole thing is mod a minus b, and this is y is to x. So this part will be y by x plus y times the whole thing.
Oh, okay, sir. I think.
Well, unitary method.
Got it, sir. Got it.
Is this fine? Any questions, any concerns, do let me know. Actually, let's do this question. No, not full day. Actually, this is the last question which I was about to give you before I go for a break. On the other side of the break, I'll talk a little bit more about internal angle bisector and external angle bisectors of two vector. And then I would start with the concept of scalar product.
Oh, okay, sir.
What, you're finding this very interesting, huh?
Yeah, sir.
Everybody would be like cursing.
No, sir, it's weird, so we'll do more of it.
Weird and hence interesting.
Yeah.
Okay. ABCD is a tetrahedron. O is any point. Okay. If the lines joining O to the vertices meet the opposite faces in P, Q, R, and S, prove that this is equal to 1. Oh, nice question. Yes, tetrahedron is just to give you that A, B, C, D are non-coplanar points. Yes, any idea, anybody?
Two minutes, sir. 2 minutes.
Yeah, sure. See, clearly these four are going to be linearly dependent, right? What did I tell you? 4 vectors or more than 3 vectors will always be linearly dependent. Correct? That means one can be expressed as a linear combination of the other two. That means there would exist scalars, not all 0, such that this can be expressed as a null vector. Right? This is the very definition of a system of vectors being linearly dependent. Oh, after that you are stuck. Okay, let us try to together solve it. Now, if you look at this expression, can I write it as YBZCTD equal to negative XA? Correct? Right?
Yes, sir. Then y plus z plus t equal to minus x.
Yeah, that's what I wrote here. Now do one thing. Let us divide by y plus z plus t. Okay. Now, here is a statement that I'm going to make over here. See what is happening over here. Let us make the diagram. This is the base of the tetrahedron. Okay. So there is a point O. There's a point O. What they're trying to say that if the line joining O to the vertices meet the opposite faces, I could take it in such a way that it meets somewhere. Okay, let me take somewhere over here on top. So if I connect this and I extend it downwards, okay. Now see here what is happening. Let's say O is here. Just for your understanding purpose, I'm drawing it in such a way that if I extend it downwards, so it is passing through O and coming downwards to meet the opposite face over here. Now, if you try to relate this scenario with this condition, do you realize that this is a scalar times A, right? This is a vector in the plane of BCD. Do you understand that? This is what? This is a linear combination of BCD. Linear combination of BCD means it will be a vector which is coplanar with the joint with the BCD, right? So it will be somewhere over here. And this is also in the straight line connecting OA.
Where is O? Oh, okay.
O is somewhere over here. Correct. So basically it is trying to say that your left hand side is a position vector of a point on the plane of BCD. Why am I writing planes? Plane of BCD. Correct? And this is trying to say that it is a point on AO extended or AO vector or OA vector, whatever you want to call it. Why I'm saying minus away? Because you are reversing the direction actually. Yeah. Is this fine? Okay. Correct. And let's say this is the point P for us, that point P that they are talking about. Meet the opposite faces in PQRS. So it is justified that the point OP for us that they are talking about is minus XA by y plus z plus t. Correct? So what is AP vector now? AP vector will be OP minus OA, which is nothing but minus XA by y plus z plus t minus OA, which is A itself. So if you simplify this, it will give you minus x minus y minus z minus t times A by x plus y plus z, y plus z plus t, which is negative of x plus y plus z plus t by y plus z plus t times A. So can I say this ratio's first expression, that is OP by AP, OP by AP, OP by AP, can I write it as, this by this, which is actually clearly x by x plus y plus z plus t, right? Now I'm sure with the very first expression you would have got an idea about what would the second ratio, third ratio and the fourth ratio lead to, and I think you're smart enough to guess that OQ by, what was the other ratio? OQ by BQ. What will this be? Y by x plus y plus z plus t, right? Similarly, OR by CR will be z by x plus y plus z plus t. And finally, OS, that's what they're calling it, right? OS, yeah. OS by DS will be this. So if you add them, you are clearly going to get, 1.
So, but then O should change its position, no, sir, each time.
Huh? No. That position I had made because it was convenient for you to imagine it. If it is not, it could be extended plane also.
Oh, like how, sir?
It could be extended plane also. For example, let's say if I kept it over here, let's say, right, and I connected it to C, correct? Then the opposite face to this was this, and you have to extend it backwards to see where it goes and intersects it, or go behind. Are you getting my point? So let's say this plane, if I extend it more further, let's say this was your plane, right? So you had made it a bigger plane like this, and you had connected O to C and extended it backwards, then it would have cut over here.
Oh, okay, sir.
Yeah. So
can it be internal also?
Huh?
Can it be internal also?
It can be internal also, it can be extended plane also. Here it is internal because if you're extending it, it is cutting it over here on the plane. You don't have to extend it somewhere.
No, sir. I meant can O be internal also?
That's a very good thing to actually assume. If O is internal, then probably it will definitely meet all the planes internally. Yeah, of course. Let's say I keep my O inside over here. This is my tetrahedron. O is here. So OA extended backwards will meet here. This will be a P. OB extended backward will meet over here. This is your Q. OD extended backwards somewhere over here will meet R. Got it? Similarly, for OC extended backward will meet on the plane ABD, which I cannot show because it appears somewhere over here. Correct?
Oh.
Okay. O can be internal, O can be external also.
Yes, sir. Could you go down, sir? Slightly, yes, sir, yes. Yes, thank you, sir.
Fine then, dear students, let's take a break because we had a very hefty exercise on vectors. Right now, as per my watch, it is 6:30, but I will give you some grace seconds, 6:31. Let's meet at 6:46 p.m. Okay, in the introduction to vectors, we have some more concepts. I think one more concept to be covered, and then we can start with dot product. Enjoy your break.